Krakatoa. Okay, and if we're looking at this guy, so I'm going to do all the A's first. So if A is my reference angle, opposite, adjacent, hypotenuse, the sine of A is going to be 5/13. The cosine of A, adjacent over hypotenuse, is going to be 12/13. And the tangent of A is going to be opposite over adjacent, which is 5/12. We're going to change our reference angle to be B. B, now our opposite, adjacent, they change. That's going to be the sine of B is going to be 12/13. The cosine of B is going to be 5/13. And the tangent of B is going to be 12/5. So we're not ever going to use the right angle as a reference angle, because then things get kind of confusing, because then your hypotenuse is also like your opposite side. So we usually only use the other two angles as our reference angles. Now, you should be seeing some kind of special characteristics that are happening here. Notice that these two values are the same, and that these two values here, the sine of A and the cosine of B, are the same. And there's a special reason for that, is if we have 180 degrees in a triangle, and we already know that one of those degrees is a 90. What would the other remaining 2 degrees have to add up to? So what would A and what would B have to add up to? Well, if we already know that there's 180 and we've already counted for 90, that means that if we did 180 minus 90, that A and B would have to add up to be 90. So A and B are actually complementary. Okay? And that's special because sine and cosine are called cofunctions. That means the value of sine for one angle is equal to the cosine of the other acute angle. So for this guy, the sine of A is 12/13, and the cosine of B is also 12/13. So since A and B are complementary, that means they are 90 degrees. They are, I just said this, complementary. That means they have the same trig ratio. So if we let one of the angles be x, like looking down here, if one of the angles is x, let's just give it a specific case. So if this is 60, we know that this one would have to be 90. So if now we say it's x, and the reason we knew it had to be, if that's 30, then the other one would have to be 60. And the reason we knew that it was 60 is because if we do 90 minus 30, that gives us the 60. So if we want to put a generic case on it, if x is A, then that means that C would have to be 90 minus x, the other acute angle, so that those two angles add up to be 90 degrees. So if we're looking at this quickly, if angle A is a measure of 30, that means angle C would have to be a measure of 60. If angle A is a measure of 45, angle C would have to be 45, because we want those two angles to be complementary and we want them to add to be 90 degrees. So some kind of examples, some weird notation that you might get to see is that if the sine of theta is 4/5, so this would be 4 and 5, that means the cosine of the 90 minus theta would also be 4/5. Similarly, if the cosine is 11/27, the sine of the other angle that is complementary to cosine of theta would also be 11/27. Now, if we look back up here, you'll notice a pattern between these two tangents as well. Those two tangents were reciprocals of each other. So those aren't the same values, they're actually reciprocals because the opposite and the adjacent switch places. So if the tangent of 1 is 4/5, the tangent of 90 minus theta would also have to be, or would be the reciprocal would be 5/4. So it flips that fraction. And it says, for example 2, find the sine of, if the sine of 28, if the cosine of 62 is 0.469. So you'll notice that if I take 28 plus 62, that gives me 90 degrees. Since those two angles are complementary, that means if I have one sine and one cosine, that those two values, so the sine of 28, will also be 0.469. Same ratio. So even though this time it's written as a decimal, it's still going to be a ratio. It's going to be a proportion. Okay, so it says find the value of theta for which sine of theta equals cosine of 15. Again, if we want those ratios to be congruent, we need these angles to be equal to 90 degrees. So if I did 90 minus 15, that's going to give me 75 degrees. Okay, and I think C and D are pretty much similarly patterned, so I think you can find those values on your own, and just make sure to reach out if you're still struggling with that cofunction idea. The reason that we use Pythagorean theorem is that it sets up the missing side length. So you guys know that we can use Pythagorean theorem here to solve for a missing hypotenuse. So if I have 4 squared plus 3 squared equals c squared, 16 plus 9 equals c squared, which is going to be 25 equals c squared, so c is 25. So this is one way that we know how to find a missing side length. But what happens when I only give you one side length and one angle? That's what we're going to be learning next time. And we can always use a calculator to approximate a ratio. So we have some of the actual ratios that we know based on the unit circle, but you can also just plug into your calculator. So if you have a calculator in front of you, plug in the sine of 47 and see what you get. It should give you a ratio of 0.731. Again, this is kind of like having the fraction, but in this case, I'm just leaving it as the decimal approximation. So sine, cosine, and tangent are above the 7, 8, and 9 on a TI-30 calculator. We're going to be using sine, cosine, and tangent, and we're also going to be using that little green notation behind the sine, cosine, and tangent, which is the inverse sine, inverse cosine, and inverse tangent. So we're going to be working forwards to solve for side lengths. We're going to be working backwards to solve for angles. So give these last couple a try. And if you did pull up this video on your computer, watch that. It is a fun little song just to help you remember SOHCAHTOA. But again, SOHCAHTOA means the sine of the angle equals opposite over hypotenuse. The cosine of the angle equals adjacent over hypotenuse. And the tangent of the angle equals opposite over adjacent. Okay, good luck with your trig ratios. Remember, we